Columbia. This is part of a series that's being put on part of the Regional Adaptation Collaborative. My name is Jim Vanderwall. I'm with the Fraser Basin Council, with support here from my colleague Manes Dovedo. We're fortunate to have financial support for this webinar and our other efforts here from Natural Resources Canada, as well as support from the BC Ministry of Environment. Sea level rise is a hot topic in BC, as we know, and we've got a great group of people here today, fully subscribed for our webinar package. Our speaker today is Thomas James, who is a scientist with Natural Resources Canada. He's with the Geological Survey of Canada in Sydney. And Thomas has had an interest in sea level rise over his career over the past 25 years, and will be giving the presentation on the new projections. Just for those that are, I guess, familiar with the provincial guidelines related to sea level rise and sea dike construction, this is what you're hearing today is an update on the basic science that's behind those guidelines. So it's when the provincial guidelines were developed a couple of years ago, they were based on some science that was done in 2008 or so. So this is an update on that science based on the new IPCC report. And Thomas will have some more to say on that in a moment. So at this point, we're going to pass the baton over to Thomas, and he'll take us through the presentation.
Okay, well, Jim, thank you very much. And I guess the first question I would have, has the views switched over to my, there we go. It should be showing now, the title page.
Not quite there yet, we're just give us a moment. Okay, yeah.
Oh, very good. Okay. Well, I'll assume that everyone is able to see my title page. And with that, thank you very much for the introduction, and thank you for the opportunity to speak on sea level projections in British Columbia. A few weeks ago, I gave a presentation that discussed the projections Canada-wide, and today is an opportunity to focus in on British Columbia. And by the way, I live in Victoria, and I work at the Pacific Geoscience Center, which is part of the Institute of Ocean Sciences on Patricia Bay. And this is a picture of the coastline at Patricia Bay. So some acknowledgements for the work that I've been doing. This is an activity in our Climate Change Geoscience program. We're partnered with the Climate Change Impacts and Adaptation Division and working on a national coastal report. And the CCIAD people that we interact with a lot and that I want to acknowledge are Don Lemon and Fiona Warren. The report that was released last fall, the title is given here, and my co-authors were all at NRCan at the time that they helped me with this report: Joe Henton, Lucinda Leonard, Andrea Darlington, Don Forbes, and Mike Kramer. Lucinda is now a professor at University of Victoria, and Andrea has moved on to become a scientist at Environment Canada. A measure of the electronic age that we live in, Mark Carson is at University of Hamburg. I've never met him in person, but I'm indebted to him for his assistance with the IPCC data and various files that I worked with to generate the projections. And finally, I'd like to thank Jennifer Pouliot and Jim Vanderwall for providing this opportunity to speak at today's webinar. So, as Jim said, my talk today is going to describe new projections of sea level change. It's based on the latest science, and it's for information and discussion. But my talk today is not about new guidelines for BC. Jim and I both felt it was important to be clear on that. So the outline of my talk, I'll briefly mention the existing guidance on sea level rise in BC, and then we'll take a look at the IPCC process and the results of the most recent assessment report, and then how these things need to be put together in order to generate local relative sea level projections, and then finally we'll compare the new sea level projections to the BC guidance. And so starting by looking at the existing guidance, this is taken from some climate change adaptation guidelines that were published by the BC Ministry of Environment, specifically with reference to sea dikes and for considering coastal flood hazard land use. And what it boils down to is that in considering construction level, being cognizant of potential flood hazard, one needs to consider a number of factors. The first one being the future sea level rise, future sea level change. But then there are some other factors that also play into it. The tidal range, how much the magnitude of a potential storm surge, and to say something about that, you have to kind of define a typical storm that you're designing against. Need to make some statements about how big wind waves will get. And then finally, it's always prudent to build in some freeboard. And so my focus today is only on this first term, which is the future sea level rise allowance. And the guidance that British Columbia presently provides is given by this red line here. And it basically suggests that at 2050, one ought to allow for 50 centimeters of sea level rise and 1 meter of sea level rise at 2100. And there's an important proviso to that. You don't just use this red line as given, you want to correct for local vertical land motion. And the idea there, of course, is that, you know, for the sake of argument, let's say that global sea level does rise by 50 centimeters at 2050. But if in that same time frame, land has risen by 20 centimeters, then the amount of local relative sea level rise that's experienced is only going to be 30 centimeters. And that's given in a little more detail in this slide, where I use an example of Campbell River. Rounded off to the nearest millimeter per year, it's rising at 4 millimeters per year, and that gives you 20 centimeters of land rise in 50 years and 40 centimeters in 100 years. And what that does is it offsets the global sea level rise to give the local sea level rise allowance that one would compute for Campbell River. I'll emphasize that this is just an example. I've actually rounded off the uplift rate just to make the math straightforward. The actual uplift rate, I think, is closer to 3.7 or 3.6 millimeters per year. So that's the existing guidance, and what we'll now do is take a look in some detail at the new projections of sea level change, and then, as I said at the end, we'll refer back to this guidance. So let's start by looking at the climate scenarios of the 5th assessment report of the Intergovernmental Panel on Climate Change, and for conciseness for the rest of today, I'm going to call this the IPCC AR5, and probably also just the AR5. And the way that IPCC works is that on a periodic basis, every 5 or 6 years, they release a series of reports that they call assessment reports. The most recent one came out beginning in the fall of 2013, known as the AR5, with the physical science basis released in September, and then working groups 2 and 3, impacts, adaptation, and vulnerability, and then mitigation of climate change, being released in the following months in early 2014. Now, an important change of the AR5 is that the projections are now based on representative concentration pathways, which are known as RCP scenarios. And the RCPs are pathways through the century of atmospheric carbon emissions. So it's not just sort of saying, well, we're going to have so much CO2 in the atmosphere by the year 2100. It's actually specifying how that carbon dioxide is delivered to the atmosphere through the century. And for those of you familiar with earlier IPCC reports, you'll recall that the earlier reports employed so-called SRES scenarios, where SRES stands for Special Report on Emissions Scenarios. And here's some rough equivalency between the earlier SRES scenarios and the new RCPs. So this A1FI, with FI standing for fossil fuel intensive, is equivalent to RCP 8.5. And then B1, which was sort of the minimum emissions scenario in the prior assessment reports, is equivalent to RCP 4.5. RCP 2.6 is new. It's not represented in the earlier reports, and it features very stringent emissions reductions. So stringent, in fact, that by the end of the century, there would be more carbon dioxide being taken out of the atmosphere than being put into the atmosphere. And it was developed in part because of questions arising around the discussions of the Copenhagen Accord, where there was an idea that global atmospheric temperatures should be kept to 2 degrees Celsius. And then a question became, what do we need in terms of an emissions scenario that would let us meet that 2 degrees Celsius target? So here is projected increases in global temperature shown for 2.6 and for RCP 8.5, where we're keeping it down to about a centimeter. This is a starting point of 2000. Excuse me, a centimeter, a Celsius for RCP 2.6, but 4 degrees Celsius for 8.5. So a fairly substantial range in the projected increase in global temperature. Over on the right, you'll see this again. This is the mean over 2081 to 2100 for the 4 scenarios, and you can see there's a pretty steady progression from 2.6 up to 8.5 of the increase in global temperature. So what does the AR5 say about global sea level projections? And just a quick reminder, we know that global sea level rose through the 20th century. Here are estimates by 3 different groups of authors. This figure is reproduced from the AR5. Sea level rose at about 1.7 millimeters per year through the 20th century and the first decade of the 21st. That's the average rate of increase. Over the last decade or two, sea level has risen at a substantially increased amount in excess, larger than 3 millimeters per year. And there are several contributors to global sea level rise, and in general order of importance, the first one is that the ocean absorbs heat, and the surface layer warms and expands. This is known as the steric effect. The second is that glaciers and ice sheets experience enhanced surface melting and also accelerated discharge at outlet glaciers. And then the third is that there are some contributions from man-made activity from groundwater extraction and construction of water reservoirs, where the water reservoirs actually holds water back. And as more of those are constructed, that actually contributes negatively to sea level rise, or it contributes to a small amount of sea level fall. The magnitude of this third bullet is not large, though, compared to the first two. And here we see how that breaks down. Again, here we are, 2081 to 2100. These gray rectangles are the average relative to the starting time frame of 1986 to 2005 for 2.6, ranging on over to RCP 8.5. Average amount of sea level rise, just under 40 centimeters at 2.6. rising up to slightly over 60 centimeters for RCP 8.5. And I'll just point out, in terms of the individual contributions, they're given down here. The red crosses is the thermal expansion or the steric effect. That's the largest contributor. The next largest is mountain glaciers and ice caps. That's the light blue. Greenland and Iceland are these smaller amounts down here, with fairly large uncertainty from rapid dynamics of the Antarctic ice sheet. And so again, that's not the surface mass melt, that's glaciers flowing into the ocean. And here is a different way of looking at the projected increases in global sea level, where we have an envelope for RCP 2.6 and for RCP 8.5 through the century. The solid lines would be the median projection. And this envelope is from a 5% to 95%. So they basically show what we call is the 90% confidence range. And we can see that we're committed to at least 25 centimeters, a little more than 25 centimeters of sea level rise by 2100. And at the upper end, the 95th percentile of RCP 8.5 is almost a meter of sea level rise. It's 98 centimeters. Oops, excuse me. And on the right here again, we have this mean, the mean values with a projected sea level change. And then the final thing that I've put on this graph is the BC guidance. So here's the 1 meter at 2100 and 50 centimeters at 2050. And similar to the original guidance, I'll go back. I think it's worth pointing out that the original guidance, the 2050 value also lay a little bit above this projected median value, whereas by 2100 it was coming into the envelope. So here we are back at the global projections of global sea level change. One additional important point, these envelopes of projections, they're considered likely. And I've italicized that because that's how the AR5 handles some of these statements. And likely means a probability of 66% to 100%. And a question immediately arises, why aren't these projections kind of, you know, the full story? Why are the probability of these projections, you know, potentially as small as only 66% likely? And part of the answer to that, there's some aspects of the climate system that are poorly understood. And with regard to sea level change, an important component is the stability of the West Antarctic ice sheet. And this is a fair amount of text to slog through, but it's a direct quote from the AR5, and it says that only the collapse of marine-based sectors of the Antarctic ice sheet, if initiated, could cause global mean sea level to rise substantially above the likely range during the 21st century. And then they go on to say, there's medium confidence that this additional contribution would not exceed several tenths of a meter of sea level rise. So the AR5 gives projections of likely sea level change, and they make some statements about how much bigger global sea level rise might be. What they do not do is provide an upper bound. This is a challenge for people who are concerned about planning and so on. And in fact, it's been criticized already in the scientific literature that the AR5 sort of stops short of making some statements about potential upper bound of sea level rise. What we did for our purposes, we adhered to the AR5 as closely as we could, and in addition to the RCP scenarios, which I'll be showing you projections for, we constructed one additional scenario by assuming that West Antarctica contributes an additional 65 centimeters of sea level rise to RCP 8.5. And the 65 centimeters comes from the average of 4 values that are quoted in the AR5 if you dig into the details of Chapter 13. And so this additional scenario gives a total of nearly 140 centimeters of sea level rise by the year 2100. Just a very quick comment. My focus today is on sea level projections to the year 2100. There is information out there on what sea level might do beyond 2100. We're at the low end, the dark blue. If we can stick to an RCP 2.6 kind of scenario, global sea level rise could potentially be held to below 1 meter. But on the other hand, up at the RCP 8.5 range, there's a potential for several meters of sea level rise in the next few hundred years. So now we've discussed the global sea level projections. Now let's consider further the local, the factors that affect local relative sea level projections. And so, excuse me, I've already alluded to this when I discussed the BC guidance, but I think it's important to come back to it again. That global sea level change, it's really saying what the global oceans are doing relative to the center of the Earth. But what one cares about is local relative sea level change. What is sea level going to do relative to a solid piece of land? And the key factor for moving from global sea level change to local relative sea level change is the vertical land motion. And there are also some other factors that affect regional projections. The dynamic, ocean currents generate a certain topography to the ocean surface. And if those ocean currents are projected to change, then the elevation of the ocean surface is also projected to change. And that's called dynamic oceanography, or dynamic oceanographic changes. And then when glaciers and ice caps melt or discharge ice to the ocean, the meltwater is redistributed in a non-uniform way because the shrinking ice cap its gravitational attraction to the ocean water surrounding it is changing, and so the surface of the ocean is actually changing its elevation due to gravitational effects. And so these, all three of these factors are incorporated into the new projections, and let's look at them in just a little more detail. So here's vertical land motion across all of Canada. Large uplift rates around Hudson Bay. The uplift rates decrease, and you actually get small amounts of subsidence in some parts of the Maritimes and Newfoundland. Over here on the west coast, most of British Columbia is rising at 2 to 4 millimeters per year. Fraser lowland, and in particular as you move into Puget Sound in Washington State, the land is actually subsiding at small amounts. And the land uplift is, looking over all of Canada, the differences are large enough and the uplift rates are sufficiently large that it actually leads to projections of sea level fall, for example, for areas around Hudson Bay. And we'll see that in a moment. The land is rising more than fast enough to offset the projected rise in global sea level. Looking at the changes to ocean currents and how that affects sea level, in eastern Canada, the Maritimes, and also the Beaufort Sea, dynamic oceanography is projected to contribute 15 to 20 centimeters, 0.15 to 0.2 meters to sea level rise by the year 2100. The story is a little more cheerful on the west coast, where dynamic oceanography, if anything, might contribute to a very small amount of well, a negative contribution to sea level rise of 0.05, 5 centimeters or less. So dynamic oceanography, in terms of long-term steady changes to sea level, is not projected to be an important factor in British Columbia. What is more important in British Columbia, and of course that's factored into the guidelines, is the strong changes in sea level elevation that are experienced through an El Nino southern oscillation cycle, where sea level can change by several centimeters over a number of years. So here's looking at the meltwater redistribution factor again, where what is shown here is Antarctic source, Greenland source, mountain glaciers, and ice cap source, contributing on average 1 millimeter per year to global sea level rise. And what you see, looking at the middle panel, for example, is that close to the source, which in this case is Greenland, sea level is actually projected to fall. And then as you move further away, sea level is projected to rise, and at particular locations, it will rise by even more than the average 1 millimeter per year. This dark orange is 1.2 millimeters per year. So what happens in Canada, that because of our proximity to Greenland, and also because we have mountain glaciers in the coast mountains, and we're also here on the west coast, relative proximity to the Gulf of Alaska, that contribution to global sea level rise locally is actually a negative contribution. It's a sea level fall. And for Greenland, well, for the local coast mountain glaciers and Gulf of Alaska glaciers, that is a contribution to sea level fall. For Greenland, the 1 millimeter per year contribution translates into only about 0.6 or 0.7 millimeters of sea level rise. And so what this does, this meltwater redistribution, is it because of our proximity to these ice masses, it actually reduces the local projected amount of sea level rise. So now we have all the ingredients, and now let's put them together to look at the new relative sea level projections for BC. And just quickly again, here are three graphs of the vertical or up GPS time series over a number of years. Halifax, it's running from the beginning of 2002 to the end of 2013. Quad was installed near the beginning of 2006. It's rising at nearly 4 millimeters per year. Here's a site on James Bay, La Grande 1, that's rising at nearly 15 millimeters per year. And so this was, these uplift rates from GPS were folded into the sea level projections. And here are the projections for all of Canada, where the large uplift rates around Hudson Bay lead to projected sea level fall, whereas in the Maritimes and also in BC, the land is rising at smaller rates, or in the case of the Maritimes, it's sinking, and it leads to larger amounts of projected sea level change. And zeroing in on BC in a little more detail, we have small uplift rates, southern Vancouver Island and the Fraser Lowland, subsidence in northwestern Washington State, and then most of the remainder of Vancouver Island and much of the mainland coast is rising at 2 to 4 millimeters per year. And then when you go further north, Prince Rupert and Sandspit on Haida Gwaii have small vertical motions. And so we'll see that these observations of vertical land motion and the pattern of vertical land motion is replicated in the sea level projections. So here we have projected sea level. This is the 95th percentile of RCP 8.5. So it's the top of the red envelope in previous pictures that I've shown you. And uh, um, largest sea level projection where there was the subsidence here in northwestern Washington state. Slightly smaller amounts of projected sea level rise, southern Vancouver Island and Fraser Lowland. And then this broader area has some of the smallest amounts of projected sea level rise where the uplift rates are the largest. And then up here in the north, we go back to the orange color again because the uplift rates are smaller. And so how does this compare to the BC guidance? And so here, just focusing in on Campbell River, the figure very much follows the previous formatting and color coding and so on, where these rectangles, for example, are the 2081 to 2100 means. Oops, excuse me. Oh, here we are. I lost my mouse for a second. And the red lines show the projected median value for 8.5. The light blue is RCP 4.5, and the dark blue is RCP 2.6. The green triangle is the West Antarctic scenario, where we added an additional 65 centimeters from West Antarctica to the median value of 2.6. And so you'll see that the purple circles are the BC guidance, where I took those values and I adjusted by the appropriate amount of vertical motion. And you'll see that in all of these locations, and in fact this would be true of all the sites in BC, the values lie a little bit above, sort of 10 to 20 centimeters above the red triangle, and they lie well below the green triangle that is the West Antarctic scenario. So what does this, what implications might this have for the BC guidance? And so I guess, you know, to recap, their new projections, they're based on the AR5. They incorporate the up-to-date estimates of mass change, the steric effect, as well as some new effects that were not incorporated in earlier projections. And we can say that the BC guidance lies above this likely projected RCP value, and it's consistent with a precautionary principle that in the light of uncertainty, it may still be necessary to take some action. And we can remind ourselves that the RCP projections are likely, and that projected sea level change could be larger. And from a physical standpoint, we come back to this possibility of a larger contribution from West Antarctica. That's exemplified, for example, in the green triangle and this West Antarctic scenario that we developed. The literature, the scientific literature now has a number of examples of expert elicitations, which are sort of structured interviews of experts, mainly glaciologists, some physical oceanographers, on what they think probable upper bounds of the contribution from West Antarctica are. And these expert elicitations consistently suggest larger amounts of sea level change. And there's an annex at the end of this presentation where I give one or two references. And then in addition, there's a literature of sea level projections using a method called the semi-empirical method. And these projections were assigned low confidence in the AR5, I believe for good reason, but the literature exists, and the method projects larger amounts of sea level change than the process-based RCP projections. So the BC guidance allows for some of this potential additional sea level rise, you know, at the level of again, looking at the top of the red rectangle here and moving up to that of about 15 or 20 centimeters. So I think this is a point for discussion, but I would suggest that this suggests that current guidelines could be retained, but that one would continue to monitor scientific progress in understanding the upper limit of projected sea level change. And with that, I'll just close to my summary. So relative sea level projections based on the AR5 have been generated for nearly 60 locations in Canada and 17 in British Columbia. The open file report is available at this URL, and I believe that that URL has also been put on the discussion panel that everyone should have access to. We're presently working on a second open file to give detailed tables of projected values. That open file is nearly ready for submission, and I would hope it's available by the end of April. And so with that, I'll stop, and I'd be happy to answer some questions.
Great. Thank you very much, Thomas. It's very interesting and in-depth look at how these projections may affect British Columbia. So for those that are on the webinar, if you have questions for Thomas, please feel free to type them into the question box or the chat function, whichever is easier for you. As Thomas has noted, there is a link in the chat box where you can download the report. We will also be making a recording of this webinar available after to you or to others, and the presentation. So you'll have the link there as well if you wish to go into the details of Thomas's report. Okay, so we've got some questions coming in here, so I'll just we'll start here. First question is, I believe I saw a projected rise of 80 to 100 centimeters on one of the maps, but about 30 to 40 centimeters in the graph. Which one is correct?
Would help if I knew which location that was for.
Yeah. Question. Can you maybe clarify here whether you're if there's a specific location that you're thinking about? In Vancouver.
In Vancouver. Okay, so let's have a look. So here's Vancouver. That's the median projection. The 95th percentile is going to be up about here, okay, about 85. And I apologize, the envelopes are not shown, and that's one of the reasons we're doing the second open file report, is to give detailed tables that give the 5% and 95% values. But anyway, you know, the top of the rectangle is the 95th percentile of the average from 2081 to 2100, and it's coming in about here. The 95th percentile at 2100 is going to be a little bit higher. It's going to be up around 90 centimeters. So let's go take a look at the map now for Vancouver. I think we're good. It's 90 would put you right in the middle of this orange. So I hope that answers the question.
To answer the question, basically it sounds like it's the difference between the median and the 90th percentile that you're
exactly. Yes. There. Yes, and this figure here that people are now looking at is showing the median values, not the 95th percentile.
Okay. We have another question here. As a scientist, what would you suggest for policymakers regarding the importance or not of reducing GHG emissions as soon as possible?
So I think that the thing to realize, or perhaps if I can kind of turn that back, and it's I'll just add that when I started doing these projections, data was available for RCP 4.5 and for RCP 8.5. The RCP 2.6 was not available, and it was only by approaching Mark Carson, and over the course of a few months, that information became available. I personally felt that it was important to show the full range of projections, so that you can take a look at an RCP 2.6 projection and say, okay, well, sea level is only going to rise by 20 centimeters, say for the sake of argument. And here's an 8.5, sea level is going to rise by 60 centimeters. And then it would enable policymakers it would give them the information to make some judgments about relative costs of active mitigation versus the costs of eventual adaptation. So, there are costs related to mitigation, but the downstream benefits would perhaps be that global sea level rise would not be as large, and that would potentially save on some costs of adaptation. So, I don't want to answer the question directly, but I would point out that this range of projections, gives the kind of information that one needs, to make some decisions or to examine some different scenarios about costs of mitigation versus costs of adaptation.
The next question is, why is most of the rise toward the end of the century?
Yeah, and that phenomenon has been present in the projections for quite some time. I mean, we can even see it in the BC guidance, where this dotted median line was taken from a synthesis of some of the available scientific literature at the time, and you can see that the rise between 2000 and 2050 is not as big as the rise between 2050 and 2100, and then it accelerates perhaps even a bit more. And basically, there are it takes time for there's sort of lags or sort of absorption factors, I guess, in how the heat gets absorbed and how it translates into, for example, melting, surface melting. That surface melting is actually fairly direct. If the atmosphere warms, then surface melting of glaciers will rise concomitantly. But it takes time for heat to get absorbed by the ocean, and then the warm water circulates underneath ice shelves, and that causes ice shelves to thin, and then they eventually collapse, and then you get enhanced ice discharge of outlet glaciers, and there's sort of that whole process is not instantaneous. So there's some lags built into it. And then I think the other thing is that I didn't show I didn't show a figure of the actual concentration of greenhouse gases, but for some of the scenarios that rises faster toward the end of the century. So it's a combination of a number of factors for why things speed up toward the end of the century.
A question about the West Antarctic ice sheet. Is there more research available on the probability and ramifications of the possible loss of the West Antarctic ice sheet?
Yeah. There will be. I'll just make an observation, first of all, about the AR4. So that was the previous assessment report. It identified some real some issues, some areas of where there was a lack of understanding, and some of that lack of understanding was just we didn't have the right kinds of observations. Some of it was that the appropriate modeling, that advances in modeling hadn't been, or advances in understanding how to model hadn't yet been incorporated into the models and then sort of carefully evaluated. So following the AR4 there were 2 or even 3 really major efforts by American and European agencies to get a handle on some of these things, and with, I would say, a great deal of success. And as one sort of practical example, air missions, planes were flown over the West Antarctic ice sheet to map the thickness of the ice and to understand what the bedrock topography is. And you need that information if you're going to model glacier flow. So there are a lot of advances in understanding that are incorporated in the AR5. And what the AR5 has done is kind of come out with this one really resounding area where we don't have as good an understanding as we would hope, and that's the stability of the West Antarctic ice sheet. And that's got to do, by the way, with the fact that much of the West Antarctic ice sheet, it's actually sitting on bedrock that is below sea level. And so as ice thins, it starts to float, and then as soon as it floats, it in essence is an ice shelf, and then if there are warmer ocean waters, that ice shelf can break up quite quickly. And it's thought that there's a potential for sort of a runaway effect where the thinning leads to floating, and then the floating ice is rafted away or melts quickly, and then that allows even faster flow, more thinning, and so on. And so that process was, or that hypothesis, or really, you know, a kind of an idea about the stability of marine-based ice sheets, was put forward in the mid-70s, and it's you know, it's a tough problem. You have to sort of drill cores through kilometer-thick ice sheets to try to get an understanding of the basal conditions. You want to understand precipitation patterns over the Antarctic ice sheet as best you can. So, you know, there's lots of challenges there, and it may not be as readily amenable as some of the problems were from the last, from the AR4, but I'm hopeful that we'll make some progress in the next 5 to 10 years. But if the question is has anything come out between the time that scientific input ended to the AR5 and the present, I have to say I'm not aware of anything yet, but I anticipate a lot of attention being paid to this question in the next few years.
Okay, next question is, does the subsidence in mid-U.S. indicate that this land would be flooded and stay flooded, i.e. not usable?
Jim, could you read the question again? I didn't catch the first.
Yeah, I'm not sure which part of the mid-U.S. the person's referring to, but it says, does the subsidence in mid-U.S. indicate that this land would be flooded and stay flooded?
Yeah, so the person might be referring to the east coast of the U.S., where the land, sort of a stretch of land from probably New York City south to the Carolinas, is probably sinking at 1 or 2 millimeters per year. And so what that does is that that contributes a little bit to local sea level rise for exactly the same reasons that we've been discussing for BC. And then the other thing about the east coast of the U.S., and this is just some stuff that's come out recently, and there's been some online articles, you know, media attention paid to it, is the potential diminution of the Gulf Stream, and then because of the dynamic topography that the Gulf Stream generates, if the Gulf Stream gets a little bit weaker, then there could be a little bit of enhanced sea level rise as well. But it's not, you know, it's not factors of 2 or like orders of magnitude bigger. It's just the U.S., parts of the east coast of the U.S. are susceptible to larger amounts of sea level rise than you might expect from just the simple global projection.
Sure. Well, it's great to see we have lots of questions here, so we'll try to get to as many on them as we can before 11:30, and if we don't, perhaps we can provide those to Thomas and get answers back to you. The next question is, do you know if any research is being done on the possible impacts of changes to ocean floor tectonics due to added weight of water over the long term?
Yeah, I think for that the incremental change in the weight of the ocean water is probably could be considered to be minor. I'm not sure that would be an important factor for tectonics.
Okay. There's a question on storm surge. The original the El Cinco Sandwell 2011 report for BC indicated that information on the North Pacific was very limited related to storm surge, but concluded that storm surge would likely be lower than average. This is a question from Graham Farstad. He followed that guidance in preparing the 2014 BC flood policy report. The latest IPCC document indicates that storm surge was likely to increase globally, but did not comment on the North Pacific. Can you comment on this?
No, it's not my area of expertise. I guess my thought would be that some of my colleagues at Fisheries and Oceans here at Institute of Ocean Sciences would be much better positioned to comment on that. And if the person would like to give me their contact information, I could put them in touch with someone.
Sounds good. Maybe an interesting topic for future webinars as well. Next question, Thomas, you mentioned that empirical evidence was given less weight in ARC. Can you elaborate a little on his? Our models versus empirical.
Right. So, this is the semi-empirical projections, which I really, with the exception of that one slide near the end, right here, I really didn't discuss that at all. So what the situation was 5, 7 years ago, 8 years ago, is that there was the gap in understanding sea level change in general there were bigger gaps in understanding sea level, and one of the gaps, for example, was that estimates of global sea level rise from tide gauges and satellite observations didn't agree. So that would be a sort of observation of a direct observation of global sea level rise. And what that should do, that number should agree with the sum of the various contributions. So there would be an estimate for the steric contribution, an estimate for mountain glaciers and ice caps, an estimate for Greenland, an estimate for Antarctica. And when you added up the individual estimates, it fell quite short of the direct observation of global sea level. And there were some other issues with understanding some of the various contributors of global sea level change as well. At the time, inventories for mountain glaciers were quite incomplete, and there were some real questions about whether that contribution was really well understood. So a person named Stefan Ramstorff at Potsdam in Germany developed a so-called semi-empirical method for projecting sea level change, and he decided to sort of try to take a step back and in essence take a sidestep and avoid a lot of these uncertainties by making the assumption that global sea level rise was correlated in a fairly simple way with global atmospheric temperature. And he developed, assumed a certain relationship, tuned it against the observed record of global sea level rise and atmospheric temperature change over the 20th century. And then he took the various projections of future atmospheric temperature and made projections of future sea level change. So that is the semi-empirical method. And it's kind of sideswiping or sidestepping, these quite complex computer models that are gridded and that look at the interaction between the ocean and the atmosphere and ice sheets and so on, and consider the amount of heat that's coming in from the sun and the amount that's reflected back out versus the amount that's retained. So he was avoiding all of that, and the numbers that he came up with were much larger. They would typically projections using the standard IPCC methodology. The projections come in under 1 meter. Many of the semi-empirical projections were as big as 1.5, and in 1 or 2 cases even approaching 2 meters of sea level change by the year 2100. So a number of people jumped on that bandwagon, and there's now a fair literature on the semi-empirical method. But one criticism is that their scatter, the projected sea level change, varies quite a bit more than between the standard, what we call process-based models, which are these complicated computer models. And then another criticism, and I feel that this is an important criticism. I'm not personally very enthusiastic about the semi-empirical projections, is that they can't be, because of the simplicity of the relationship, they can't possibly capture all the very important physical processes that are taking place. All the transfer of heat between the different components of the atmospheric system, of the climate system, and indeed within each component of the climate system. I think, so the criticism is that they vastly oversimplify what is actually a very complex system. And so I think the AR5, the chapter, the people who wrote chapter 13 of the AR5, they had some other reasons as well, but those were 2 of the main ones. And in general, I'm in agreement. I understand why they came up with this assessment of low confidence. Scientifically, I agree with that, but my understanding is, from a planning perspective, one might want to give the semi-empirical projections lower weight, but you don't necessarily, if you're contemplating something that's very, very high risk, something that's going to be around a long time, you don't necessarily want to discount that those larger values of projections. That's a criticism that's been leveled against the AR5, is that by refusing to address this question of an upper bound to projected global sea level change, they avoided what is in fact a very important question. So I hope that answers it. That was a long answer to a short question.
Well, thanks very much, Thomas. We are at 11:30, and so I think in the interest of everyone's time, we'll close things off. There are some additional questions that we haven't gotten to, and so we'll make our best effort here to provide those to Thomas and hopefully get answers back to you if you by email afterwards. But I'd like to first of all thank Thomas again for his in-depth presentation and look here, and I think there have been a number of topics that have come up that might be useful for future webinars and work. There is a post-webinar evaluation. Please fill it out. It'll either pop up on your screen or you will also get an email in the next day. But we really appreciate your feedback, in particular on topics that would be useful to you, but also how you found this webinar. So thanks again, and for those that are participating on March 31st, we do have another webinar on extreme precipitation. There's a little bit of space left still for registration, so you can follow the same, there's a link in the same email that you probably received to register for this webinar if you're interested in that topic, atmospheric rivers and extreme precipitation in British Columbia. So thanks again, and we'll hope to have you involved in future webinars as well.
Well, thank you very much, and thanks for the opportunity again to speak today.
Thanks, everyone. Have a good day.